Welcome to this video that will be used to discuss absolute value inequations. Now this is simply an extension of absolute value equations, where the difference being in equations we're solving for specific x values that work, whereas in inequation we're looking for sets of numbers that may work. I'll go through the different types of scenarios that we can run into, but what you're going to find is the process that we use to solve these. We're only going to work with linear inequations. The process is very, very much similar to the way we solved equations, with a little bit extra that we have to do in terms of set work. All right, so here we go. So here's an example of an absolute value inequation. So obviously the difference is, rather than an equal sign, there's going to be an inequation symbol here. So if I want to solve this, much like with equations, the process gets complicated by the fact that if you had a negative value in here or a positive value in here and then applied these absolute value bars, you would end up with the same result, because the absolute value in both cases switches it to positive. So we have to navigate those and examine. We'll call it case 1. And case 1 would be, what if between the bars was some positive value? So the first thing we got to do is figure out, well, what would make that happen. So between the bars is the expression 2x plus 6. And I want to figure out what would make that turn out to be a positive value, bigger than or equal to 0. Solve this inequation. So x would have to be a number bigger than or equal to negative 3. So if that is the case, I put a number in here that's bigger than or equal to 3. This will be a positive value. And if this turns out to be a positive value, then we really don't need the bars, because they don't really do anything to numbers that are already positive. And then I would just solve this like I would a normal inequation. Bring your 6 over. X is less than 1. Now here's where it's a little bit different than an equation. In an equation, this would be x equals 1, and then you would just look and say, well, is it bigger than or equal to negative 3? If it is, you'd say yes, that's a solution. With an inequation, what you need to do is find all the possible values of x that are smaller than 1, but also then meet this criteria. So the easiest way to do it is to visualize it on a number line. Imagine you had negative 3 here, and then you had 1 here. Well, all the numbers that are bigger than or equal to negative 3 would be represented by that set of numbers. All the numbers that are less than 1 would be all the numbers represented by that set. Well, what we're trying to figure out are all the numbers that work here and also here. Well, the word "and" when you're talking about sets of numbers, it leads to what we call an intersection of sets. And the intersection of sets is a fancy term that just means, where do the sets overlap each other? Because when they overlap, that means, so you'll see the blue and the black, that means it's a number that works in the blue, or in the blue I guess was this one. That means it's a number that's a set of this, but it's also a number that's a set of this. So that would be where this and this are both true. So what we're trying to pick out is where these would overlap each other, which would be right in here. So that's the set of numbers that are bigger than or equal to negative 3, but at the same time, they're also less than 1. So this notation means every number between negative 3 and 1, including negative 3 because of the equal sign. The reason I include it is because this one's shaded in, and this would also be included, so it includes that for both sets. But over here, it's not included in both sets, only one of them. The black one it includes, but not this one. So in order for it to be an overlap, it has to be part of both. So that's why there's no equal sign on this one. All right, well then the other possibility would be, what if, so I'll call it case 2, would be, what if between those bars were a negative value? So I need to figure out what would make that happen. So what would make between the bars less than 0? Solve this inequation. X has to be now smaller than negative 3. Now, if between the bars is a negative, from our previous studies, we already know that in order to switch that to a positive value, the same way that the absolute value bars would, without using absolute value bars, is to take what's between the bars and multiply it by a negative. Because if it's negative and you multiply by a negative, that will switch it to a positive, the same way that the absolute value bars would want us to do. Leading us to this new inequation. Negative 2x minus 6 is less than 8. minus 2x is less than 14. Divide by a minus 2. So remember now, if you divide both sides of an inequation by a negative, you must reverse the inequality. So x has to be greater than negative 7. So what I want now is to determine what numbers are bigger than negative 7, but at the same time they're also smaller than negative 3. That'll give me all the possible x values that would work in this case of the analysis of the absolute value. So negative 7 would be to the left of negative 3 because it's smaller. So negative 3 would go there. I would want all the numbers greater than negative 7. That's all those numbers. I want all the numbers less than negative 3. That's all those numbers. Then I want to know, well, where did those sets intersect or overlap each other, which would be right in there. Those numbers are true on both sets. That would be every number that's between negative 7 and negative 3. So at this point, you should be getting comfortable with writing out this set notation. Okay, so the final step in the process is taking the two solutions. So this could have happened, or this could have happened. Again, talking about sets of numbers, when one set of numbers or one other set of numbers could have happened, we call that a union of sets. And a union is where you just join together the two sets. So what that simply wants us to do is take our answer we got from this case, and join the two together, mesh them together on a number line. So I always like to just kind of put down here final solution. Put a number line. So this set of numbers was from negative 7 to negative 3. So again, just the overlap. It was there to there and everything in between. So that was case 2. Case 1, when I join it and put it on here, is everything from negative 3 to positive 1, including the negative 3. So I'll just put it in a different color if you want. So this is case 1. So it said now to fill this in and go over to here, but don't include this one. Now when you look at that, all joined together, when you do a union, you're not looking for intersection or overlap. You're looking for just what was the end result when you joined the two together and put them on a single number line. Well, the end result, you can see, is everything from negative 7 over to 1. So my final answer for this inequality is any x value that's, any x value that's bigger than negative 7, but it has to be smaller than 1. So remember, this implies all the numbers between negative 7 and 1, not including negative 7, not including 1, which is exactly what I'd be looking for. All right, so what I'd like to do now, just go through a few more. There are some different types of situations you can run into. Let's take this one. I think this is just a kind of straightforward one. So now that we have the process down, I'll go a little bit quicker. Remember, you can always feel free to pause the video and try it on your own or rewind it if you don't understand something. This one, I would say case 1 between the bars could be positive, so I need to identify what would make that happen. So greater than or equal to 0. Negative 2x would have to be greater than or equal to minus 5, which would only happen if x was, now I got to divide by a negative 2, that's why I'm going to switch the symbol. So x must be smaller than or equal to 5 over 2. If between the bars is positive, I don't need the bars because they're not really going to do anything. And I just solve this inequation. So minus 2x is less than minus 2. Dividing by a negative both sides, x will have to be greater than 1. This would be, so 5 over 2 is 2.5, so that's here. And 1 is here. So greater than 1 is all of those numbers. Less than or equal to 5 over 2 is all of those numbers. So these two sets overlapped right here. So that means that 1 is less than x, right? No equal sign because it's open. But here it's closed in, so we're going to put an equal sign. There's what I get out of case 1. Now the number line is there just for your own purpose, your own kind of personal purposes. if you have a good grasp of these and you feel I don't really need to draw this, that's fine. You don't have to draw this. You can just write out your solution here. Or some people even like to wait till the very end and just piece it all together on one number line. I'm not sure I'd suggest that. That's kind of a lot to try and keep track of at once, but if you're comfortable with that, I'm fine with that too. Ultimately, we're looking for the correct final solution. So now I look at the other possibility, what would make between the bars negative? So 5 minus 2x could be less than 0. Minus 2x is less than minus 5. Again, reverse the inequality because you're dividing by a negative. X must be bigger than 5 halves. So this time's the scenario where between the bars was a negative. So in order to switch it to a positive, I'm going to put a negative through to everything in the bars. And that would be less than 3. 2x is less than 8. X is less than 4. So on a number line, 4 is here. 5 halves, which is 2.5, is here. Greater than 5 halves. Less than 4. So they overlapped in here. 5 halves is less than x, which is less than 1. Piece that together to make your final solution. So the final solution is what we call, again, the union of the sets. You join them together. So you would take, so from 1, what's going on here? Something's wrong. Oh, this is 4, not a 1. Again, this is where I miss not having my live audience to fix my mistakes when I make them. Okay, so 1 to 5 halves. This is here. So 1 to 5 halves. Include that. Then go 5 halves to 4. Open circle. So when you joined that all together, we got all the numbers between 5 halves, 1 and 4. So my final solution, and there's no equal sign, so 1 is less than x is less than 4. That would be your final solution. Okay, we're starting to roll now. Again, I got a few others here. I just want to show you that this one will be a little bit different in your end result. Doesn't change how we do it. So case 1 is between the bars may be a positive value, so I got to figure out what would make that happen. So if n plus 6 were greater than or equal to 0, that would only happen if n was bigger than negative 6. So if between the bars is positive, you really don't need them because they don't do anything. You just solve it as it's written. So we're going to solve this. 10 onto n plus 6 is greater than, I'll take that over there, it'll give me 80. I'll divide by the 10. I'll divide by the 10. N plus 6 is greater than 8. N is greater than 2. So this time, I'm looking for numbers that are bigger than or equal to negative 6. That's all those ones. And I'm also looking for numbers that are bigger than 2. That's all those ones. So you can see the overlap starts here, but it goes forever in this direction. So basically it overlapped everything to the right of 2. So from this I get any number greater than 2. Case 2 is what if between the bars is a negative? So that would be n plus 6 is less than 0. That would only happen if n was less than negative 6. So that means I have to somehow get a negative to go through this and switch it to a positive. So this would accomplish that if I just put a negative out in front of the 10, because that's going to distribute through the bars. Again, there's a variety of ways. You could leave this as 10 and put negative n, negative 6, be the same thing. Take away 7 is greater than 73. I'm going to do the same as last one. So negative 10, n plus 6. Take my 7 over, I'm going to get 80. This time I'm going to divide by a negative 10. That's going to give me n plus 6 is greater than negative 8. N is greater than a negative 14. Oh, right here. Again, my audience not there to help me. I divided by a negative 10. I should have switched my inequality. Picked up on it here. So this should have been less than, less than. Alright, so negative 14 would be here. Negative 6 is bigger than it, so it's to the right of it. Less than negative 14 are all these numbers. Less than negative 6 are all those numbers. There's your overlap. So they overlap for anything less than negative 14. Remember, this could have happened, or this may have happened. So when I go to my final solution, so n is bigger than 2. There's 2. So there's those ones. N is less than negative 14. Negative 14 is over here. There's all the numbers less than negative 14. So we've described sets like this before when we did quadratic inequalities. And we should be familiar with, there's a gap. So there's some of the numbers are here, and then the rest of the numbers are over here. So it's not the situation where you've got everything between two numbers where you start here and you end here. It goes forever this way and forever this way. So the way you describe this is any n value less than negative 14. When there's a gap in your set, we use the word or. Or this could have happened. N could have been anything bigger than 2. And that would be our final set. Now just quickly, 2 little oddball ones to watch for. Let's suppose this one. Solve this inequality. Now you could go through the whole case analysis, case 1, case 2. It'll give you the right answers. But I want us to, let's think this one through. So we're going to take the absolute value of some expression. There's nothing else here on the left side. So regardless of what I put in there for x, and then do 4 minus that number, it doesn't matter what I get in between the bars, it's ultimately going to give me some positive answer. So I'm going to try and figure out when would this positive answer be bigger than negative 5. Well, I hope you would argue and say it's always bigger than negative 5 if it's positive, which would imply this absolute value situation in terms of an inequality really doesn't require any work. All you have to do is say x could be any number, because regardless of the situation, this will be positive, which is always guaranteed to be bigger than negative 5. And again, you may say, well, I would have never thought of that. That's fine. Here's what will happen. You'll do case 1, there'll be no overlap. You'll do case 2, they'll overlap, let's say everything greater than 4. Then you'll do case 2, they'll overlap everything to the left of or equal to 4. And then when you piece the two together, it'll fill in the whole number line. So even though you may not notice the little shortcut here, your case analysis will still give you the correct answer. So don't fear that I may never think of that. And there's one more little oddball one, this one here. So it's saying take the absolute value of this expression all by itself, figure out where it's going to be less than or equal to negative 5. Well, the only numbers that are less than or equal to negative 5 are more negatives, right? They're all negative over here. But unfortunately, when I take the absolute value here, I could get nothing other than a positive result. So I'm deemed with this, try and figure out where some positive number is going to be less than or equal to negative 5. You may say, well, that can't happen. That's impossible. And you're absolutely right. That is impossible. This would be an empty set. There are no possible solutions. And we've seen that before, but I'll refresh your memory. That is a symbol that means the empty set, or sometimes called the null set, meaning no possible solutions. Doesn't matter what you put in there for x, there's no way this could possibly work. And again, if you say, I wouldn't have thought of that, I would go through my cases. You can, and all that would happen, this is the one I started to talk about a second ago. When you go to do your overlap in case 1, there will not be any, so there's nothing there. There's no numbers that work in both. Case 2, you'd go to do your overlap, there'd be no overlap. So you get nothing, empty set, empty set. Obviously, when you join 2 empty sets, you'll get an empty set. So that is a look at all of the different things that you could encounter when solving absolute value of the linear variety in equations. And we will only deal with absolute value linear equations in our studies in Pre-Calculus 11. Thanks for watching. As always, have a look at your practice questions. Once you're done your practice questions, give the formative an attempt and turn it in for some feedback. And if you have any questions or concerns, you can always reach out to me via Teams. Thanks for watching.